Aerospace Institute lecture again, and it's great to see so many familiar faces. It's wonderful that you all come back again and again, and we are always delighted to have you here. I started Rice a long time ago as a graduate student in 1971, and my husband was doing his basic training because of Vietnam. He was trying to stay out of the war, and so I had a free summer before I started graduate school. So I got accepted to both the physics department and the space physics and astronomy department, and I said, well, you know, which one should I go with? I said, who's got a summer job? And they said, well, you know, we just put an instrument on the moon on Apollo 14, and they need somebody who knows Fortran that can help analyze the data from the particle detector. And I go, so in May of 1971, I came to Rice and started working on the CPLEE instrument. And I actually didn't meet the person who had designed and built the CPLEE instrument until several years later, because he actually left Rice a couple of years before I arrived. And my official thesis advisor was David Reisner, who was one of his students. So in the science genealogy world, he's my science grandfather. So then I asked Brian, I said, well, who was your thesis advisor? Because I was getting into doing these science genealogies. And he said, oh, Sir Harry Messel. And I said, ooh, that's exciting. And I said, well, who was Harry Messel's thesis advisor? And he said, well, I don't know. Let me ask him. He was still alive at the time. He came back and said, guess what? Schrodinger was Messer's advisor. So I'm a great granddaughter of Schrodinger. So anyway, science genealogy is fun, but what is more fun is to meet the people who were really there, that did the work, whose creativity really made the science happen. And I was very fortunate to be part of the Apollo program as a graduate student. As I said, I started after Apollo landed, but I got
for that.
Oh, yeah,
Yeah, for mine.
but I analyzed data through my PhD, and I got to turn off the last experiment on the moon when they were all shut down in 1977, which was a long time ago. Anyway, this was the signature of all the people who were still around that were Apollo ALSEP PIs, and we were lucky tonight to have actually 2 Apollo science PIs. Brian is going to be speaking, and Manik Talwani of the geology department.
Just step back so that they can see you, that you don't want to be on the
So we at Rice were really excited. We had both 2 particle detectors, a dust detector and a gravity meter. So Rice was very, very important in the Apollo program, and so it's very exciting to have one of the really critical instrument builders from Rice University come speak with us tonight. So he got his PhD, as I mentioned, in Australia from Harry Messel. He went to the University of Iowa, where of course the Apollo 1 was done in the 60s, and worked as a faculty member there, rising up the ranks to associate professor. And then when the Department of Space Science here was formed here in 1963 in response to President Kennedy's talk on the Rice campus in September of 1962, Alex Dessler, who created the department, was looking for people in astronomy, astrophysics, space physics, atmospheric science to really put together the department, and he picked no better experimental space physicists
Thank you. Thank you, Pat, and thank you all for coming tonight. I want to start off with the left-hand side because this is an experiment that was written up by Tommy Gold in 1971 in the Apollo 14 preliminary science report and was forgotten or ignored for 40 years. It's on the NASA website. What happened was that they wanted to know how much, what particular substances dust stuck to. And so they built a little, much smaller than this, but if I can borrow it, about half this size, aluminium plate with a dozen stamp-sized materials, aluminium, white paint, and then a different white paint, and Velcros, and all sorts of things. A dozen of those, and Alan Shepard was instructed to just throw some dust on it, okay? And then brush it off and see what happened. But on the second panel, there are two identical panels. He was instructed just to brush it off. Now you'll see in this panel, you'll see a couple of the squares, but you'll see in white the identification numbers. Okay, they're indented and stamped in. When he put the dust on, the dust molded itself inside the numbers. And then Alan, we're not quite certain what happened, but probably he jolted the plate and the numbers jumped out cohesively. Not all of them, you know, beautiful 3s and 5s and 7s and so on. Now that was forgotten for 40 bloody years until I came in and in 2010 pointed it out. People were very fond of levitated dust for various reasons. This is cohesive dust. These are the only structures built of pure lunar dust to date. And anybody involved in STEM should carry away with it that the only numbers, the only structures built of lunar dust are numbers. If that doesn't grab your kids, then you've got problems. Okay, I wanted you to see that early because it sets the scene for a lot of the forgetfulness or ignorance of dust in the last 50 years. Okay, next one then.
Okay, you want to go to the PowerPoint?
Yes, please.
Okay.
Oh, that website there in blue has got all the references and so on, and more details that I might scrabble over tonight. If you want to enjoy yourself there, I built that last year with a mate because there are too many errors in the NASA website. And about a fortnight after I put it up, after writing to a few people, the NASA website came down for 2.5 months. And it's back up again in late November. It's removed a few mistakes, but it's still not satisfactory. So I'd go for this one. Next one. Okay, I'm going through a little bit. Pat said to go from way back. So that's me and my friends down the Antarctic, where I first saw auroras in all their beautiful divine magic and signalling, as Scott said, divine signalling. I don't attempt to show them, but we're down in the Antarctic for various reasons. One of them was to land on Oates Land, which is the last bit of Australia's claim in the Antarctic. Nobody had ever been there. We landed there. You climb a mountain, you hoist a flag, you take possession in the name of Queen Elizabeth, and you build your little pile of rocks. Now, if we've got time, I can tell you a story about that pile of rocks. Just say Uncle Frank if you're feeling bored sometime. I'll tell you my story. Next one. Okay, that's Northern Hemisphere aurora, of course, with the Inuits. And I fell in love with auroras then. I haven't fallen out of love with them. Also fell in love with Auroral. And that's the two of us in the Serpentine Gardens on our honeymoon on the way to America, to Iowa, via London. When you're an Australian PhD student, you just said, go to London, it's close to everywhere. And it really is. Next. Okay, so I told Van that I wanted to build a satellite that would look down on auroras to measure the light and would have particle detectors on it so that I could do the cause and effect stuff. I'm very strong on cause and effect. So we'd see the particles that cause the bright light, that caused auroras and so on. Unfortunately, Van got a phone call from his mates at the Pentagon that said there's a classified payload, two classified payloads going on the 29th of June 1961. In the nose cone, there's room for something else, provided it's 13 inches high and doesn't weigh more than 40 pounds. That was 5 months in the future. And so with a handful of kids, we built a satellite from scratch, which was 13 inches high and 40 pounds less 1 ounce, which I thought was rather good. It was also the first satellite that ever used digital telemetry, just by the by, and it did what it should. That's a photo of Van and me in our younger days. Next one. By happen chance, and it was a big influence on my future, the offerings I got from the Pentagon. On July the 9th, 1962, the US set off a 1.4 megaton thermonuclear device. They weren't bombs, they were all devices, which is 70 times stronger than the ones in Nagasaki and Hiroshima, 70 times. That's a photograph taken from the 1 minute and 3 minute after the bomb, taken from 1,000 kilometers away. Now the interesting point was that when the bomb went off, the burglar alarms and traffic lights in Hawaii, about 1,000 kilometers, started to go off or go out. And that was caused by an electromagnetic pulse, which the official report was rather larger than expected. I won't go into details, but that's the way it went. The electromagnetic pulse, think of it as, you know, when there's a lightning strike, you get a crack, static in your radio. There's a ground current, high voltage ground current that surges through, and an electromagnetic pulse that can set off electronics 1,000 kilometers away, of course, can do some damage. So for the next 20 years or so, it was classified until they'd worked out how to have a computer talk over the horizon to another computer. Once they did that and a bit more work, then the internet was invented. So if you want your kids to know where the internet came from, it came from Starfish orgasm on the 9th of July 1962. The Russians were doing this at the same time, but not as high and not as large. And the Cuban Missile Crisis, it's worth remembering, came later that year. And after Khrushchev and Kennedy agreed, and all was at peace, just to celebrate, the Russians and the Americans set off another sub-megaton device on the same day for 3 days, just to show, flex their muscles, I guess. This shows the serious nature, the right-hand side. This is a engine 1 measurement. And I don't know if I can do this. This engine 1 was the only satellite that measured before and after radiation effects. The radiation effects were so strong from Starfish that it zapped the solar cells of 8 satellites who stopped working. Engine 1 was the only one that did before and after. So, as it turned out, I was wanting to build engine 2 and 3 were on their way, but I got all sorts of kind offers for new payloads and from all sorts of people. After that, it made life very easy. Okay, next one. Back to what we're supposed to be doing. This is engine 3. The left-hand side is my comparison of, again, being interested in auroras. The source of the particles that caused auroras, the electrons and protons, it was early on thought, after the discovery of the Van Allen trapped radiation, it was thought that it was particles coming out of like a leaky bucket that would come down the magnetic field lines and start auroras. And people seriously thought that the Van Allen radiation belt was the source of the particles that caused auroras. But we flew with engine 1 and Explorer 12. We flew some more sophisticated detectors and showed that the estimates that Van had made early on were 1,000 times too high. We reduced the population or the density of the bucket and turned the thing right upside down, or I did. So to have a model which I call the splash catcher, so that it's actually the source of the auroral particles way out that incidentally leaves a bit of splash which causes the Van Allen radiation belt, tips the whole source, cause and effect upside down. And the next slide is engine 3 introducing a VLF. I thought that VLF pulses which bounce up and from hemisphere to hemisphere must be related in some way to trapped radiation, which does the same thing. So we built with Don Gurnett's skill in Iowa, we built the VLF experiment, and sure enough, the VLF intensity goes up as the intensity of both precipitation and trapped radiation goes up, and as the light goes up, the auroral light. I should mention Don Gurnett is one of my favorite graduate students. He's got experiments growing from that VLF, which is his first one, on Voyager. So he's out beyond the solar system with the same sort of thing that started with engine 3. Anyhow, more about that. Okay, so as Pat said, I got appointed associate director, professor, and so on. And engine 3 was a glorious, glorious bird. And I was looking for other locations, and Rice made an offer I couldn't refuse. But I wanted to show you this body language of Alex Dessler and myself, which I think tells the complete story. Alex was a theorist, you see. I'm an experimentalist. And we had many and many discussions as to who was right. And you have a look at my hand, that last hand movement in number 4. and the body language of the dominating theorist who was trying to tell me what was going on, and I was looking at measurements, and in the end it was just... And Alex went to lunch. We had some good times though. Now there are some samples of race history omitted tonight, which I'll go through very quickly, and well, they're all there. And they're only samples. If we have time, I'll elaborate on those, but I will elaborate on the right here and now. Somebody, who shall be nameless, had the bright idea that the brand new Space Science Building should be, the turning of the sod, so to speak, to celebrate it, should come with something to do with science and space science. And they said, Brian, you've got some satellites still in orbit. Can't we use a signal to trigger a shape charge to blow this up, blow the sod? I said, sure, you could do that. But having a realist point of view as to schedules of speakers at a celebration and ceremonial offering, we never did it that way. I had Ray Proctor with the shape charge, and Ray loved shape charges, did very well with them. And Peter Carey inside the laboratory with a little switch and a cable running out to the shape charge, and much more reliable. And nobody knew the difference at the time. Okay, next one, we flew some small, I'll leave the rest of those for the time being, but they're all good stories. Next one then, please. We flew some small rockets and some large rockets as we were learning. That's Dave Reesner, who was the guy who got his PhD on CPLEE. And that was with the payload, that was for protons and alpha particles for those technicians here. Next one, the Aurora 1 satellite. I don't know whether any other universities have built satellites. I guess they have. But the story behind this was, it was classified hitchhike again. They changed the orbit on us. Because they changed the orbit and made it much higher, I was worried about shielding of the photomultiplier. And I knew the new orbit. I knew how much shielding I wanted to wrap around the photomultiplier, but the whole payload had been spin balanced. And we're out at Vandenberg Air Force Base, all top security, soldier with a, he didn't have a bayonet, but he had a rifle and all that sort of stuff, watching us. And that I told Ray that I wanted to somehow or other have time to calculate the exact amount of lead that we'd wrap around it, and it was his problem as to how we did it. And we did it under the watchful eye of the Air Force man who didn't. That's why we're clustered here. Various things were happening. And it all worked beautifully. Next one. Then by this time, there was talk about Apollo and Moon and the rest of it. And a lot of us had the idea that the magnetospheric tail, that long tail there, probably could go as far as the Moon, even though it's 60 Earth radii. So I just decided to put some of our auroral payloads, double them up, make them all complicated, and put them as charged particle lunar environment experiments. And fortunately, NASA approved that. They approved 7 out of 90 proposals in the first round. And John Freeman's proposal and my proposal were both in the 7. That's me with CPLEE in, that's the Apollo 13 CPLEE actually, the one that's down in the bottom of the ocean. On the right-hand side there, by serendipity, I invented the dust detector, and how that came about was NASA insisted on the 10th and the 11th and the 12th of January 1966, the 7 principal investigators were being told how the people were going to build the bus, if you like, all the power supplies and the telemetry and whatever that would carry 3 or 4 of our experiments, each Apollo mission. And 3 companies were bidding for it, 2 of them were in LA. So they were all going through all this, and we were told that we had to put a dust cover over CPLEE where the particles would come in, so it had to be retractable after the Apollo astronauts left and the rocket fumes had gone and the rocket exhausts that presumably would stir up dust had gone. And I was quite happy about that because I thought there probably would be dust from the rocket exhaust. But I asked what I thought was a very sensible question, who's going to build the dust detector? And they said you can't have a dust detector because it'll take too much time of the astronaut to deploy and it'll be too heavy to go by existing dust detectors. It'll be 2 kilograms we're talking. And so I was very cranky and I told them that was, if you'll pardon the language, very Australian, that was bloody stupid. And I was so cranky that I got on the plane flying back to Houston. And on the plane, I had a double scotch before dinner. Then I had a sleep. And my frontal lobe somehow or other invented the dust detector out of 3 solar cells. And I scratched that up on the back of the little, what do you call it, the drink coaster. And then after I'd had dinner, on the white napkin that came with the nuts, I did a refinement of it and put some temperature sensors on the back of the solar cells. So that's cause and effect. That's one of the delights of the thing. You measure the dust by the change in voltage of the solar cell. 10% drop in voltage, for example, is about 1 milligram of dust per square centimetre, something of that order. So you not only do that by measuring the voltage, if you've got the thermometer at the back, you also measure the temperature effect. So you've got cause and effect again, same as with the engine satellites. And NASA didn't like that. In fact, NASA changed it to a microphone when they were negotiating with Bendix. But I had a few words and that died. And they came back to the old dust detector. Next one. That's Buzz Aldrin carrying the, what are we doing? I'm out of sync, am I? Yep. Okay, that's the story then of NASA insisted and so on. And that's my story of the invention. NASA had the last minute and this was the original design with two vertical cells, one of which pointed to sunrise and the other to sunset, because I thought that's when action would start to happen. And then you've got the horizontal one. NASA, in its wisdom, said, oh no, you can't do that. We'll put all 3 cells on top. And one of them, having come back to Houston, fell off. So it needs sticky tape. But the 3 were on top. And of course, only Apollo 12, which was built already, has something that looks at sunrise. And that's by far the more powerful. Of the 14 discoveries coming from the dust detectors, 12 of them came from basically the solar cell looking at sunrise. Okie doke. So we've got Buzz, next one, yep. Buzz with the deployment. Now, some people have asked me, what did it feel like in Apollo 11 actually having your first experiment? There are only 2 live experiments on Apollo 11. One was the dust detector and one was the seismometer. When the boys took off to leave, the first rocket launched from the moon, so much dust came up that the seismometer overheated by more than 30 degrees and died. Well, they turned it off after 21 days. The little dust detector sort of charged on. It could keep going up to any number of degrees. And in fact, it measured the degrees. But it also measured the dust. NASA, in its wisdom, reported that there was no significant dust degradation on the Apollo 11 dust detector. And there's various, I don't know whether you're interested in the story, you can read the story and the full story on the web now, because I've published in the web the original NASA report. The first one, which has not been published before, agreed that 2 out of the 3 cells had significant degradation, but because the 3rd cell didn't degrade, there was no significant dust. So NASA struck again, or Manned Spacecraft Center, I should say, struck again. And it wasn't for another 6 months that I convinced them to write another paper, with me as lead author this time, with the correct statement that there was significant degradation. Personally, what was most annoying is that they added my name to the wrong one without permission, which undercut any arguments I had with NASA headquarters, because I was allegedly the author of saying that there was no dust. Anyhow, back to the Apollo landing, for example, and who can remember the Apollo 11 landing? Okay, I assume all the rest were, well, I won't assume, but the only magic, or the most magic thing for me was when they're at 40 feet before landing, Buzz reported dust strikes, dust hits or words, those things. And that made my day, sort of 8 hours or whatever it was before they actually landed. I was celebrating quite happily. So I knew that the dust detector had earned its living. Next one. Oh, sorry, I should mention Buzz knew full well about all the concerns, and so he put the seismometer behind the biggest rock he could find to try to shelter it. This is only 17 meters away. Now that's a rocket taking off at that corner of the room. And so, of course, there was a lot of dust. And that was finally accepted. Yep, next one. That is the only photograph we had and the only copy we have of the NASA version with the 3 horizontal cells. That's up on Apollo 11. And Pat and I have got various devious plans which we hatched today. See how that might find its way to Rice. Next one, the right-hand side then is the actual digital evidence of the 3 solar cells. See, 17% degradation in one, 7% in another, and 0 degradation in the other. And that's in the second paper that the new paper that was authored by the same 3 authors, but with me as lead author. And that one's the correct one. Okie doke. Also in the website, I included the ballad of 2 out of 3, which I still think was rather a nice ballad that I circulated everywhere I could to persuade people that how stupid it was to say that there was no degradation when 2 out of 3 cells were degraded. So enjoy my little ballad of 2 out of 3, and remember that I wrote that within months of this nonsense that was being generated. It's actually got a bit of a rhythm, and it talks about Spiro Agnew, so it puts it into context. And trips to Mars. I think it's a damn good ballad. Okay, so the context of now from 1969 to 2019. Just to summarise what we've got there. Next one. Oh, that's the ballad. So, well, I mean, that's a comment on the ballad in that website, so look that up. Next one. Okay. Just to put you, those of you who are geeks involved in data transmission and so on, the Apollo data were transmitted 1,060 bits a second. 1,060. They're recorded for use on 7-track recorders, which are now obsolete. They're recorded on 2,500 foot of half-inch tape, each weighing about 2 kilograms, with bit density, just appreciate this, 600 bits per inch. You can almost see the individual sort of ones and zeros. And I mentioned more than 3,000 tapes were lost at Goddard during the floods and so on. The only tapes, the only original tapes from Apollo 11 were sent to me in Sydney, and they're still good. We read them again in 2012. We've got plenty of readings of all the data and spread around, and also I'm currently trying to negotiate with the Australian government, which is a very difficult group to negotiate with. You think you've got problems in federal governments, you should see Australia. We're going to have an election in 3 months, God only knows. Anyhow, I'm trying to negotiate with them and the 6 original Apollo tapes to have those donated to the American government for storage in Smithsonian or one of those places. But all the data are collected and they're widely known. Next one now, just to Apollo 12. That shows that fella with the vertical tape, vertical cell. And that second slide there is Apollo 12 as well, but just gives the context, the spatial context, the loneliness of the, I've said that's the loneliest solar cell in the solar system, really. That is the only the only measurement of sunrise from the moon that I know of. And that strikes me as being quite weird, because at sunrise on the moon, all sorts of exciting things start to happen. We can talk about that if you need to, if we've got time. Okay, now we come to the next one, is the importance of lunar dust. There's engineering importance, there's scientific importance. All the astronauts complained of the problems with dust. The website shows that in more detail from quotes from Gene Cernan, and I spent a few hours just before a year or so before he died, with Jean and we talked about dust. I would like to tell you an anecdote that Jean's recorded in a movie, which will go to any professional person who, mother or father, who has to be away when the children have birthdays or school events and whatever. Jean's 9-year-old daughter, he apologised to by scratching her initials in lunar dust, which was quite an apology. But then, of course, he didn't know how to tell her how long the initials would last. And his best effort when he hit Australia was that there's no wind on the moon, so they'll last forever. But the little dust detector, good old little dust detector, of course measures how much dust accumulates. So I could tell him it's more than 28,000 years. I tell you a story against myself. I told Jean while he was alive, more than 28,000 years. After he died, I had a bit more human approach. It's an interesting thing that the variation between the personal involvement and the science rigor, if you like. I got one of the other astronauts who was looking after the widow and the daughter to change the message to more than 1,000 generations after everybody now. And in a sense, that's what Apollo's got, you know, that mix of the involvement of the humanity. I was, in the excitement of publishing the 28,000 years and whatever, I lost sight of the humanity in talking to Jean. And I wish that I should have, that I didn't tell him more than 1,000 generations. And he could have told his daughter. Anyhow, didn't happen. Okay, and the science, and Jim Geyer is measured, quite apart from the astronaut's problem, Jim Geyer's measured 9 different types of problems that dust causes. Vision problem, not just with the visors, yeah, we're going for time. It blocked the site of the landing site for 2 of the Apollo landings and so on. Again, you can read those. Skip the next one and go to, skip that one. So that's the CPLEE, which Pat was involved with, except that's the Apollo 13 CPLEE, which is underwater. And this is the other one. Some people think it's very special. I think it's very special, but I try not to say it. I'm the only scientist that was principal investigator of 2 different experiments in 2 different sciences, 2 different disciplines on the moon, which I think is fun, but whatever. Next one. China entered the space program a few years back with the first lunar rover for 46 years, and that's little U2. And they're in it in business. The first talk that I ever heard them give was in America, and they showed all their slides in Chinese. And nobody really appreciated what that meant. But I'd been through it with the Russians, the space race with the Russians, and the Russians never did that. They always put it in English. All the talks were with slides in English. The fact that the Chinese were sufficiently confident that they should show their slides and their discoveries in Chinese showed to me, at any rate, that they're in business, and they really are in business. U2 ran for about 100 metres on the first lunar day, but it stopped after its first sunrise. And I had a theory, and I don't have a slide to show it. Anyhow, the website's got the details that at sunrise, the areas disturbed by a rocket exhaust will be activated, charged with, through the photoelectric effect, given positive charges. Since they've all got positive charges, they'll repel each other, they'll lift up from the ground, which is also positively charged, and you'll have levitated dust. And we measured all that with Apollo 12, with this one and solitary one. The levitated dust from the moon came up and landed on the horizontal solar cell, so that after the first 3 days, the accumulated dust was 1/3 of what was accumulated over the next 6 years. So it was only that shortly after the first few sunrises, whereas the horizontal cell watching the sun saw variations in sunlight after sunrise caused by dust in between it and the sun. So we had two pieces of evidence for levitation of dust, and once you are read through a model of that, and you can read about that, that explains why the moon's surfaces are smooth, despite being pockmarked with craters, and a whole lot of other mysteries. But also, for those of you who are interested, it means that there is a natural process of smoothing after disturbance, which means that a lot of the fears of mining on the moon can be alleviated. You don't have to do anything, you just wait for sunrise to take care of the disturbed area. And so on the next one, and oh yes, we'll wrap up with that. One of the things that I did for Van Allen's 90th birthday in 2004 was give him a nose cone carved from the West Australian wood jarrah, which is absolutely beautiful, golden glow when it's finely carved. I challenged a young wood turner that I knew in Denmark down south. Could he do that? And he finally made one after a lot of knotty problems, if I could put it that way, on one selected beautiful piece of wood that he'd aged. So then, and that was great for Abby and Van, they were delighted in it. Then I was invited to Beijing last year to help them out with some of their dust issues, if you like. And I thought, why not? So I asked the wood turner, can you make me another one? And he said, yes, I've still got some of that log left. And he made me another one. And so I thought it fitting to present as the exchange of presents to the designer of the Chang'e 3 and Chang'e 4 missions, the same gift that I gave Van, who was the designer of the first US satellites. So if there's any reaching across the hemispheres, you can do it with a gift, preferably from jarrah carvings from the southwest of Western Australia. That's all then, thanks, and I'm sorry it's been a bit bitty, but you got time for any questions? Or
And if you don't mind waiting for the microphone, we are streaming it and recording it. So here we go.
Hi, I was wondering, on one of the slides you had three graphs of measured brightness versus time, I'm assuming for each individual cell. The graphs, the measured brightness went up as time went on, and that's kind of the opposite of what I would think if dust is covering the cells. So I'm just wondering why that is.
Yeah, I'm not understanding.
Sun rising, I think the sun was rising. The degradation, why were they rising ahead of the time that they jumped back down here? Is it here?
Oh, that one.
Yeah, they were
No,
rising.
no.
And then the launch, they dropped down? Is that right?
What mission are you talking about? Which slide are you talking about?
So it's talking about this slide here, so the three charts. You're talking about degradation, but all of the measured brightness is increasing.
Oh,
so he's curious as to what the charts are actually showing.
Okay, sorry. Yep. The vertical, these are the three solar cells, as per that, side by side, with one's fallen off in use. Okay? The horizontal time is just in seconds there. Hours. Okay. The measurements are every 54 seconds. So you've got the vertical axis is the brightness, how many volts are coming out of the solar cell. And then the vertical line is the actual time of lunar module ascent when the rocket exhausts. That only takes about 10 seconds. So as you've got the rising in each case is due to the sun rising over the solar cells that were like that. Sun's rising, so it's looking at more and more of the solar cells, so more and more light. So they're getting brighter all the time. But then you slash the lot with dust and you get dropping there from the voltage in two of the cells, but not in the third. Okay? Now why two and not one is, if you look at the rocket, if you look at the movies of the rocket effects of dust, it's in streaks. It's very strongly striated as the dust was blown up from the chattering rocket exhaust and so on. Sorry I was slow to catch up with what. I'll switch on to sunrise effects.
First off, I want to say thank you very much for the discussion this evening. I learned an awful lot. Of the three items, you know, obviously the dust is described as very sharp and very abrasive.
Yep.
Of the three things that have been talked about potentially doing for a long-term mission to the moon that come to mind, the first is potentially taking regolith and turning them into building blocks of some sort.
Yep.
The second one is potentially using certain amount of that as a radiation cover, so basically going underground to help out radiation concerns. And then the last, theoretically, if we find the water, we hope, is finding a way to mine that water. Which of those three activities is probably going to be most hazardly and difficultly affected by the dust associated problems?
Ooh. The very access to the moon stirs up dust. And the walking of an astronaut or the movement of a rover or something stirs up dust. The dust will travel ballistically because there's no atmosphere, and it'll stick to anything and everything. The three issues you've got, the one about the cave appeals to me because I used to be a speleologist. But all three of those are underway now. In this meeting I was at this past weekend, they're all actively being pursued. And it's only now that they're starting to think of dust as being a factor in the whole exercise. It was only this weekend that I heard the chairman of the whole thing wrapping it up and said, it is now clear that any future mission to the moon without a dust detector would be, and he used various words, the way that I used various words. But at any rate, it's now accepted that it's a factor in everything you do on the moon. If you want to do any science, it's guaranteed to be a factor. If the thing gets stuck, causes your zips to stick, and it strikes, according to the description by Cernan, it strikes suddenly and irretrievably. Once it sticks, it is stuck. Once it's inside the camera, right off the camera. Because there's no way you, I mean, what do? Wipe it with a handkerchief. That's what people were thinking of. Wipe it clean. They put a brush on. By Apollo 14, they had a dust brush. Great big special dust brush. That's halfway through the whole missions. And they gave it to the lowest, the cheapest of the nomination. And it didn't work on Apollo 14, 15, 16 or 17. I mean, it brushed, but it distributed the stuff. They had a vacuum system up there, but they only had one spare bag. I mean, there really are some funny stories in all of this, or sad stories.
What do you see the differences in exploration of the moon and Mars, and the challenges of dust on both of those? How do you see the differences between those?
Well, apart from distance and travel sort of thing. The simplest way, both have got dust. The moon has no atmosphere though. So the dust is ruggedized in various ways by bombardment, repeated bombardment. On the moon, I tend to think of it as almost like cornflakes or something like that. And there's wind, there's erosion of the dust by wind effects and whatever. But the moon is very special. That's why I think I was talking today about most of the moon is inert. The top 2 centimeters of dust are active, dynamic. They're being bombarded by the atmosphere of the moon, of the sun, by the solar wind. So you've got dusty plasmas that are composed of the nuclei that formerly were in the sun a day or two previously. And so that's immensely active chemically, but nobody's explored that yet. They're nanoparticles, and nanoparticles are in a realm of their own where laws of nature are concerned. You invent new laws to whatever. And, well, it's magic stuff. So whereas the culture of Apollo was geocentric, it was Earth-centered, all the geologies were concentrated on what is different on the moon from on the Earth. And the science was similarly are the moonquakes like earthquakes and whatever. So it's focused on the Earth. My promotion now is, and has been for some time, that for the top 2 centimeters or so, you're actually dealing with extraterrestrial processes. And your thinking and your culture has to rise to the occasion in all sorts of glorious ways. You've got a whole new laboratory up there with all of these exotic happenings. We haven't started to touch on those with the I got 14 discoveries. They're the only discoveries because they were the only measurements, but we've barely begun. Yep.
Doctor, thank you so much for coming to us, and thank you for all of your incredible contributions to science and to this country and to the great country of Australia and to the world and to mankind. If you had an unlimited budget and the science community came to you and said, design the most modern dust detector you could now, what would you design?
Would that would happen? There are so many different answers, I'm sorry. But one of them is, and since we're Rice, I can let you in. I dream of what I think is probably happening there with the astronauts. I think that they were probably wading knee deep in dust, rather like ground mist, but you can't see it. But with clever cameras, with modern cameras that are in your ruddy phones, for heaven's sake, and that sort of thing, you can play that sort of game. There are lots of things you can do, but the immediate issue I've got, and I've had for 50 years, is overcoming the mindset of dismissing the importance of dust. And it finally happened this weekend. But whether it lasts this week, I don't even know. I'll wait and see.
So your detector would be visually based now?
No, sorry. What my present very modest goal is to put one of these on every landing on the moon. Because then, you know what I mean by fungible? It's things that are as good as gold you can compare, the old and the new. You would have fungible data from every new landing with a standard measuring device, and just get that base load done, and that's a couple of $100. Unless that one of them falls off like that one.
I think a camera would be good, so you could see the
some good
moving
cameras,
and other things.
a little device to occult the sun and track it up to see the movements of dust in the thing. Can you find go to, maybe I haven't put it on the,
Is it on the PowerPoint?
I
or the
want a
website?
sunrise on the website.
On the website, okay.
Go to dust stories and very
Why
good.
don't you
No,
stick-
no.
Here's the main menus.
No, I don't know whether I put on changing truth. Anyhow, I won't take up your time with questions and so on, but no, that's the early stuff. I published the sunrise effects of dust, and they're out of the done with Apollo 12 only. That's a tragedy. There's only one measurement. There are discoveries that are based on only one device, and I don't trust that. I mean, I trust him, but whatever. So many, many different ones. Let your imagination run, for heaven's sake. Wade through the website and have fun.
I think we have one question from the center here.
Yes, there was recently a spacecraft landing on an asteroid, I believe, by the Japanese.
Sorry?
There was a landing of a spacecraft on an
yeah.
asteroid. As far as dust detection, was there any were there any sensors of or presence of dust that were detected?
Well, the problem with it all depends on the size of the asteroid. Everything I said here about the moon will apply to a sufficiently large, where I can't tell you what sufficiently large means, something that's sufficiently large to have the gravity to retain dust will be airless, and you go from there. That, I think that that landing on the asteroid, I think is an exquisite sense of European intellectual delight in the intellect, if you like. If you track the story of that, step by step, having it sleep and all that sort of stuff, it's a lovely intellectual, but particularly European intellect. Different from the brute force type approach that I've had here. There's delight after delight in the way that they went about that.
So we were saying they were not in contact with you?
Sorry?
Does it mean that they did not contact you?
No, they didn't need to. They're bright people.
Time for one more.
Yes, so we really don't have any idea of the particulate sizes from the smallest to the largest.
Oh, yeah.
The mean
Yep.
value or any of those?
No, there's lots of measurements from samples that have been brought back, and so the chemical composition is known, but there are still questions as to whether it got degraded in the boxes, whether the boxes were should have been sealed to the moon's vacuum.
Okay.
But the seals were very specially constructed, but dust got in through the actual sealing. You know, if you've got a very sharp seal, if there's dust in between, you get bumps. They leaked.
Of course, this isn't telling us the relative densities or something of the dust cloud. You know.
No, all of that's pretty well known from
right.
measurements. I just haven't.
Do we use forward scattering, backward scattering measurements, things like that to, you know?
Well, you try thinking of, I don't know when you last played with a 2 or 3 year old child, but you try thinking about how you gather dust. It's like herding it.
This is what you showed this morning.
Thank you.
Sorry?
This one that you showed today.
Yep.
Showed the pictures of the different kinds of dust.
But you see the dust will stick to anything that it hits. Anything. And it's hard to get off. Certainly can't brush it off. You redistribute it with a brush. It gets inside the fabric of a spacesuit, for example, which is 8 or 11 layers, whatever it is, gets inside there and starts to wear them, so that on Apollo 16, I think, the spacesuit started to leak, which is fairly embarrassing on the moon. All the oxygen pressures went down. Every time we went outside, the oxygen pressure was less.
I think there's a really interesting example of that. A few years ago, we had Alan Bean give a talk. I don't know how many of you were there. He was part of Apollo 12. He walked on the moon with Pete Conrad. And he also flew in Skylab. And he tells us a nice story is that when he comes back, he gets a piece of his suit cut out with a patch on it and handed to him in a plaque. And the Skylab one was pristine white. And the moon one was a bit of a kind of greyish colour, and they sort of realised it's because it was impregnated with lunar dust up at the chest patch. So he smashed the plaque and started cutting it up, and he mixes it in. He's an artist by this point. He mixes it in with his paint. So many of Alan Bean's paintings actually have moon dust embedded in the paint. And unfortunately, he passed away a couple of years ago too. But anyway, so there's lots of really interesting stuff. There's a lot of science still to be done. A lot of activity focused on going to the moon, landing on the moon, either commercially or via government entities. And I think there's a lesson to be learned from what we've heard tonight. So please join me in thanking tonight's speaker. Thank you.
And since I'm an Australian and a former professor here, can I have the last word? Please open my website and enjoy it. And there might be arrangements made for questions to be channeled through from Rice that I think is underway and be answered on the web.
And we'll also have a recording of this talk is available on our YouTube channel. For those of you who come here, we much appreciate it. But it is available online if you want to revisit some of what you heard tonight. So hopefully we'll see you on April 4th.